somebody is bowling at a bowling alley. So we'll draw this and we'll do two cases at the bowling alley. So here is the lane. And we'll say that there's a pin here in the middle. And we're going to do one with just one pin. Say this is all the other pins are gone and there's just one pin left. So this is the bird's eye view of that pin. I'll draw the side view here. And so we've got a bowling ball coming down here with speed VB1. And then it hits the pin. So I'll draw that. So we have the top view up there and then we have the side view down here. So then the pin is going to go off with some speed of VP2. And then the bowling ball is also going to be going forward. Some speed VB2. So if we're given, we need the mass of the bowling ball. We need the mass of the pin, initial speed of the bowling ball, coefficient of restitution. Find the post-collision speeds VB2 and VP2 after collision. Now this is another central impact. So we're going to assume that everything is collinear. So we'll put our X direction here along that line of impact and our Y direction perpendicular along the plane of contact. Now we know in a situation like this, the bowling ball weighs a lot more than the pin. So there's no way that the bowling ball is going to rebound and go backwards. So we know that both of the speeds will be going forwards post-collision, or really going to the right. So then when we do our problem and get our mathematical answer, we're going to have to see if it's reasonable. And we know that the bowling pin should speed up. It should be going faster. The bowling ball should slow down a little bit because the pin got smacked really hard. And because it's lighter, it should end up going faster than the bowling ball. So let's use that as our reality check, and then we'll work this math out. So mass of a bowling ball, a common mass for a bowling ball is 5 kilograms. So this is 11 pounds. They can be more or less. The heavier ball will make the pins go faster. It'll hit the pins harder. But if you're too weak to roll the heavier ball, then you may as well go with a lighter ball. And that way you can make it roll faster. So then that would result also in a faster pin speed. So then the mass of the pin, 1.5 kilograms is mass of bowling pin. That's a standard pin. And then the speed, we'll say that the speed is 7 meters per second here, that it's the initial ball is rolling at. And then E, coefficient of restitution, 0.9. So it's pretty high. It's not an energy conserved situation, but it's still very high. And we need to find these post-collision speeds. So we'll say in this situation, there is only momentum is conserved because there are no external forces. The collision force is an internal force, or between the, it's basically the normal force that happens in between the bowling ball and the bowling pin. So we will say that momentum is conserved from 1 to 2. So we need to write our momentum equation and our E equation. Now the pin is not moving pre-collision, so we know that VP1 is just 0. But we'll write everything out and then we'll cross out what we need to. So mass of bowling ball V bowling ball 1 plus mass of pin V pin 1 equals mass of ball V B2 plus mass of pin V P2. And then we also need our E equation, and I'll write that over here. E equals negative VB2 minus VP2 over VB1 minus VP1. And then we'll go ahead and cross out this VP1 because that's 0. And here, 0, because the pin is static before the bowling ball hits it. So now we can go ahead and fill in numbers. In this case, we'll get two different equations. So the mass of the bowling ball is 5. The speed of the bowling ball is 7. And then that equals the mass of the ball, which is 5 times VB2, plus that pin mass, which is 1.5 times VP2. And then if we multiply this 5 and the 7 together, this is equals 35. So next we'll fill in numbers for the E equation. And so E is going to be 0.9 time or equals negative VB2 minus VP2. And then this is divided by VB1, which is the 7 meters per second. So if we rearrange this, we'll have 0.9 times 7, which equals 0.6. Sorry, this is 6.3. And then that's going to equal the negative VB2 plus VP2. We have this plus here because the negative sign right there canceled with that negative sign. And so now we have two equations, and we can solve these either by substitution or elimination. Now, since we have coefficients that are not 1 in front of these from the momentum equation, the easier way to solve it is going to be substitution. So we'll rearrange one equation, this one down here at the bottom, solve out for VP2 in terms of VB2, and then we'll plug that into the top equation and solve out for VB2. So I'll just write here, we're going to solve E equation for VP2, and then we will plug into the momentum equation, solve for VB2, and then plug back in the E equation, solve for VP2 actual number. So if we rearrange this here, then we'll have VP2 equals 6.3 plus VB2. And even right here, we can do a reality check. So this is telling us that the post-collision speed of the pin is the post-collision speed of the ball plus 6.3. So the pin is going to be going faster than the ball after the collision. And that makes sense because if you think about it, when you're at the bowling alley, the pins just fly as soon as they're hit by the bowling ball. So we'll take this now and we will plug this back into this top equation. So we've got 5 VB2 plus 1.5 times 6.3 plus VB2 equals 35. So we just took this, we plugged it right into there. So 5 VB2 plus 1.5 times 6.3 plus 1.5 VB2 equals 35. And then we rearrange, let's see, we should multiply this 1.5 and the 6.3 together, and that will get 9.45. And then finally we have the 5 plus the 1.5, which is 6.5, VB2 equals the 35 minus the 9.45, which is 25.55. So what do you get for VB2? Put that in a calculator. Okay, so VB2 equals 3.93 meters per second. And so the ball was originally going 7, and now it's slowed down to about half its speed, so that makes sense. Now we have to plug these numbers in and solve for VP2, which equals that 3.93 plus the 6.3. So 10.23 meters per second equals VP2, which is a high speed and much larger than VB2. So reality check tells us success. Yes, this is a reasonable answer. Pretty normal that when you're bowling, you don't hit the pin dead on. You hit it at an angle. And so we're going to redo this problem as an oblique impact collision. And we will see with the same exact numbers, how will that affect the post-collision velocities and speeds of each one? All right, so from the top view, we've got a bowling ball coming with speed VB2 or VB1. And then the bowling ball hits the pin at an angle here. And this pin goes out with a speed VP2 here. And the bowling ball is going to go at some angle VB2. We know this angle here is beta, and we'll say beta equals 45 degrees. And again, we're given mass of B equals 5 kilograms, mass of P equals 1.5 kilograms, and VB1 equals 7 meters per second, and E equals 0.9. We need to find, and then we'll say that over here, beta equals 45 degrees. This is an oblique collision. Okay, so we're going to find now post-collision velocities. So VB2 and VP2. All right, so we've got our diagram here. And now we need to set our coordinate frame. So we'll say that the line of impact, we know the line of impact is in the direction that the pin traveled. So just like on the problem up above, the pin traveled along the positive x-axis, which we put to the right. That's because it got hit coming from the left and pushed to the right. So here it gets hit at some angle at the beta equals 45 degrees angle, and then it moves in that particular direction. So that is our line of impact. That is X, line of impact. And now the Y direction. So this is our plane of contact. And we will distinguish this from our general, we'll say that's I hat direction, and our J hat direction from what we had before. So what we know of to be a certain direction. Okay, so Now we're going to use, we know that in the x direction, here, we'll say x, momentum is conserved, and in the y direction, velocity is conserved. So we need to break up the components of the incoming velocity into x and y. And then we'll be able to then use the x equations and conservation of momentum in E to find post-collision velocities. This is the direction of the x, and then the y here. And if this angle right here is theta, then that means that this angle is also theta. Well, that's beta, so we'll call this one beta 2. So these are both the same angle. Those are both 45 degrees. Now, we left out here that even if we had messed this up, sine and cosine are the same for 45 degrees, but this is the correct way to draw. So if that angle is ever not 45 degrees, make sure you can get which one is correctly supposed to be beta. All right, so we will first find our velocities. So we will break up VB1 into the x component and the y component. So VB1 x is going to be VB1 cosine of beta, and then VB1y equals VB1 sine of beta. And I'll draw that a little bit bigger down here. So we've got VB1 coming in this way. And then we've got our x direction going that way. So this is positive x, this is negative x. And we need to now break up our VB1 into the sine and cosine, or this way is the y direction. And so here is negative y. So VB1 is going this way, and here is beta. Then we'll have this part in the y direction, and then we'll have this component in the x direction. So this is VB1x, and this is VB1y. And it goes that way, and this goes this way. So if you flip your head upside down, then you can tell a little bit better, but the VB1x is the adjacent side to the angle, so that's cosine. Cosine is opposite over adjacent, and then sine is opposite over hypotenuse. So that's how we get these. So if we go ahead and plug in the numbers here, we have 7 cosine 45 degrees, and then 7 sine 45 degrees. And it is 4.95 in both. So 4.95 meters per second. So we know that because velocity is conserved in the y direction, this means that VB2y equals VB1y, and that equals the 4.95 meters per second. So we've got the y component for VB2. Now we need to work on the x components. So in the x direction, we'll have momentum conserved, and we'll have the E equation. So conservation momentum, we've got mass of B, the B1x, and that equals, we're going to leave mass of P, VP1 out because VP1 was 0. So then we'll just continue mass of B, VB2x, plus mass of P v P2. And P2, VP2 is only in the x direction, so we don't necessarily need to put an x on it. That's all of its velocity is going in the x direction. And then we've got the E equation. E equals negative VB2x minus VP2 over VB1, and then it would be minus VP1, but VP1 doesn't exist. So we can rearrange this and get E VB1x equals negative VB2x plus VP2. And we can go ahead and plug in numbers here. So we'll have MB is 5 times the VB1x, which we calculated over here was a 4.95, equals 5 VB2x plus 1.5 VP2. And, let's see, over here, 0.9 times VB1x was the 4.55 equals negative VB2x plus VP2. So 2 equations, 2 unknowns. So now I'm going to give you all a few minutes, solve these 2 equations, and come up with values for VP2 and VB2. 24.75 equals VB2x plus 1.5 VP2. And then the 0.9 times 4.55 is 4.455 equals negative VB2x plus VP2. So rearranging this, we have 4.455 plus VB2x equals VP2. Now we've got this VP2, so we'll go ahead and plug that in over here. So we've got 24.75 equals 5 VB2x plus 1.5 times 4.455 plus VB2x. And then we have 24.75 equals this 5 VB2x plus a 1.5 VB2x gives us a 6.5 VB2x, 6.68. Okay, so rearranging now, then we get 18.07 equals 6.5 VB2x Good. Okay, so a lot of people got that. Very good. So 2.78 meters per second equals the VB2x. And so then we take that and we plug it back in over here, and we'll have 4.455 plus 2.78 equals VP2, 7.24 meters per second equals VP2. Now the 7.24 is at an angle of 45 degrees here below the horizontal. So we'll just go ahead and write that at 45 degrees below horizontal. VB2x and VB2y, we need to combine those. So using Pythagorean theorem, we know that VB2 equals square root of the VB2x, which is 2.78, squared plus the VB2Y, which is 4.95. So good. So 5.68 meters per second equals VB2. But now we've got to find the angle for that. So looking back up here, we have the VB2, and then I'm going to draw this in a different color so it's easier to see. So the VB2 is going off at some angle. And we can first find it relative to this y-axis. So we'll find we have the y component and we have that x component. So drawing that over here, we'll have here now is the VB2. And then we've got VB2y, and then the VB2x. So first, let's find this angle, because that's the angle that we can find, and we'll call that gamma. And then we will have to subtract to figure out if this is the horizontal direction, and we know that this is beta. We can find that final angle, but first we need to get the gamma. So gamma equals the inverse tangent of the x component divided by the y component. So it's different than y over x because, again, this angle is relative to the y-axis and not to the x-axis. So that's why we'll have VB2x over VB2y. Okay, so put that into a calculator. Remember to keep it in degrees, 29.3 degrees. So then finally, to get our ending angle, and we'll call this here theta, we'll have theta equals 90 degrees minus beta minus gamma. So theta equals 90 minus the 45 minus that 29.3, and that gives us theta equals 16 degrees. So finally, our final VB2, we'll say VB2 equals 5.68 meters per second at 16 degrees above the horizontal. And we can see here, that means that the ball did not deviate nearly as much as the pin did. So the ball is still mostly going straight. It's now just at an angle of 16 degrees instead of at an angle of 0 degrees, but the pin went off at 45 degrees. So this should make sense because the ball weighs a lot more than the pin, and the ball had the momentum to begin with, so it's going to go as straight as it possibly can, and the pin is just going to flip out to the side. Okay, so just to kind of recap what we did here, then this was an oblique impact collision. So we took the initial velocity, we found the line of impact, which is in the direction of velocity change, so the direction that the pin traveled. Then we put 90 degrees to that as the plane of contact, where there's no velocity change, so we can say the velocity is conserved. And then we split the initial speed of the ball into the x and the y components along that x direction and y direction. The y direction, we hung on to that velocity because it's the same before and after. The x direction, we used conservation of momentum and the E equation with the pin. And so we were able to solve out for VB2x and pin velocity. We already knew the angle of the pin because it was given in the problem. And so then we used that x velocity of the ball with the original y velocity of the ball to find the final speed and the final angle.